Nipa or Pooja, anyone of you start?
This call is now being recorded.
Okay, thank you. Good evening, everybody. So we have with us Professor Runa Kumari. She has, I just start with her brief description of our biodata. Professor Runa Kumari had received her PhD degree from National Institute of Technology, Rourkela in 2014. She is presently working as an associate professor at the Department of Electrical and Electronics Engineering, BITS Pilani, Hyderabad campus. Her current research interests include microstrip antenna, dielectric resonator antenna, and its applications, antenna arrays and its application, reconfigurable antennas, metamaterial EBG antennas, rectenna for RF harvesting, conformal antennas, 3D printed antennas, SIF filters. Professor Runa Kumari is a senior member of IEEE. She has also served as a visiting researcher at San Diego State University, where she worked on reconfigurable DRA antennas and their feed design. Additionally, she was a visiting researcher at National Aerospace Laboratory NAL at CSIR Bangalore, focusing on the metamaterial based DRAs. She has published over 26 SCI journals, more than 46 conference papers, both in India and internationally. She holds 1 patent and 4 book chapters and 1 book as an editor. She has supervised more than 10 PhD students, 4 of whom are already awarded and 1 has submitted the thesis, which is under review. So with this brief introduction, we have our expert Dr. Kumari, who will be handling this session of the second last day of this Hotel FDP. Her topic you can see here online. So I would like to thank Dr. Kumari for being with us and handling this session for us. And I thank the participants for being here. And I hope you can have a healthy discussion. Over to Dr. Kumari.
Yeah, thank you so much, Professor, for nice introduction, and good evening to all the attendees. So I am Runa Kumari, and this session is on antenna and RF circuit for radio frequency energy harvesting application for energizing low power devices. So my main the topic is for low power devices, and it is actually I'm going to discuss on meta surface based this one the topic. I will just show you my topic. This is actually the FDP topic, and I am going to discuss today an overview of meta surface assisted retina for RF energy harvesting. So before starting my discussion, I will just show you a small that few pics of my institute and my lab. So this BITS Pilani, Hyderabad, those who are nearby Hyderabad, they already know that it is in Hyderabad, which is actually a little bit far from Hyderabad city, not exactly in Hyderabad. You can say that 30-40 kilometers from Sikandrabad railway station. So this is actually the aerial view of our institute. You can just see here, this is only the academic block. Actually, the campus is having all hostels and faculty houses, but I'm just showing you this academic block where we have total 12 number of departments. And here actually one more closer view. And this is our entrance of BITS Pilani Hyderabad campus. Just because why I am showing you that, if you know someone is there nearby our campus and you want to visit our campus, so you are always welcome. And this is our library in Hyderabad campus. These are a few classrooms, because I am also the in charge for these classrooms and timetable and examination division. That's why these are a few pics when I am starting some introduction to our classrooms for the students. So I am using these pics. So this is our auditorium. When we are having some workshop or some conference, we are using that. And also every Saturday evening, we are having some movie screening. So you can see that the first floor for students, and then the ground floor for students and first floor for faculties. So this is actually every Saturday we screen some movies for students and faculty, because we all staying in the campus, which is very far from the city. So we should have some that relaxation time for us and our family. So this is actually the view from my balcony. Means this is actually all that faculty quarters are there. This side you can see these hostels are there. And the academic block from aerial view, which I have shown you, that is this side. And from my balcony, I have taken this picture in the evening time, because sometimes some outsider, they wanted to see you people come to visit our campus in the daytime. So that's why in evening time I have taken this one. So this is actually all about my campus, and this is actually my lab. So in Hyderabad, as I told you, that we have total 12 departments. Out of 12 departments, one department is our AAA department, which is combining electrical and electronics department. We have electrical courses. Also, we offer electronics communication. And we have 3 master programs in embedded and in microelectronics and communications. And along with that, many PhD students. Currently, the ongoing PhD students numbers are 70 to 80, that is full time. And with that, some part-times are also there. So this is our lab, which is laboratory for antenna, microwave and e-beam devices and application, which in shortcut we have given the name LAMLA. So here we will see total 4 faculties are there, those who are in means completely in microwave area, and 6 other faculties in optical area. Some are in some electrical, which is related to our microwave. So we have this last 5 years, but this slides which I am showing you, this is actually last semester I prepared for presentations. So this semester we have not updated these slides. So these are our completed, ongoing and proposed project. R&D labs, these are in collaboration with this lab and industry collaboration, we are having some projects. So these are some antenna from our that lab, which we have done. This one is actually I designed during my PhD time, the log periodic dielectric resonator antenna. And there are some circuits which from other faculties students have designed. This one reconfigurable antenna, 3D printed reconfigurable antenna. Means graphene we have used. It is designed by one of my BTech students. This is one of the output of my project, which we have delivered some mode converter to our RCI lab, that DRDO RCI lab, which is in Hyderabad. So for them, last year, we have delivered this one, the mode converter. And this is again my antenna, which I have designed in San Diego State University, the reconfigurable dielectric resonator antenna for circular polarization. So this was designed by me. This is my first PhD student in long back in 2020. He defended his thesis. So his work, which was a metamaterial antenna. So that's why you know that always the first student is very close to us. So that's why I am having this antenna still with me. And this is our lab actually. We have PCB fabrication facilities, anechoic chamber, which is having up to 40 gigahertz. And we are having this vector network analyzer, 2 vector network analyzer. One is 2-port up to 13.6 gigahertz. And the other one is 4-port VNA, which is 43.5 gigahertz. We have signal generator, spectrum analyzer, power meter, gas meter, and the upcoming facility, that is a high power measurement test facility, which was actually funded by BARC. So this was actually, this installation is not completed, it's going on. So maybe within this semester we are going to complete. So that picture is not there. Otherwise, all facilities picture are here. So actually that lab is a 2-floor building. A separate building is there. It's Lambda lab. The ground floor is having all this facility measurement. The top floor is having a place to the sitting arrangement for PhD students. These are again some software facility which we have. the IDS, console, MATLAB, CST, and HFSS, and also AWR. And these are the faculty who all are involved in our lab. Actually, you can see Dr. Lalit Kumar is a professor of practice. He was the retired director from DRDO. Recently, he joined last semester with us. And we all are here from different areas. And this is the projects completed, that mode converter just now I have shown you, that RCI we have given. These are some other, this one actually it is again my project only, that PLDRO which we have given to DLRL in 2021. So this is some projects completed output. And these are the PhD students. Again, these PhD students already, here it was written ongoing, but they have already completed because it's a, I think 1 or 2 semester back, we have taken this data. So he is my first PhD student. Then again, he is my student. And I'm going to present now his work, which he worked on RF harvesting, energy harvesting. Again, this is actually current, he is working with me. And C1 submitted her thesis last semester, but we already got the results, and next week she is going to deliver, is going to give her viva. And he is also a student of me, part-time student who worked on circular polarized DRA. And then he published, we have actually filed one patent and it was accepted. So here actually part-time students are also working very good because they are getting all the supports from our lab. We have some technician in our lab who can always help all the students. So why I am showing this PPT? That because if someone is interested, your master, some good master students are there and you can send for PhD students, then they are always welcome to our institute. So this that outreach activities we have conducted some workshop in 2019, 20, 23. So always in 1 or 2 years we conduct some workshop. So these are pictures of some workshops. So next time if you are interested, I have all the mail ID because Anirban sir always he's saying to all the mail IDs. I may that share that if in future we are going to conduct some workshops, then I will share these things with all of you. So now I will just start my discussion, today's discussion. Actually, today I am going to discuss design for wireless energy harvesting using some partially reflected surface and some artificial magnetic conductor. So we have in this area, the topic we have worked many designs, but it's not possible to complete 1 hour all the designs. So I have just selected 2 of the topic which I will try to complete within this 1.5 hours. So first actually we are going to discuss what is this energy harvesting, how it is going to help us. So as you all know that nowadays in wireless communications, most of the devices are based on wireless communication. So these wireless data services, as it is growing, the demand for power is also constantly increasing. So that is actually creating a problem with this battery life. So it is not possible to have battery for all that what nowadays we require. So what will be the solution for this? So people are doing research on that, and the solution is energy harvesting. One of the solution is energy harvesting, where what we can do that some suggestions are there that we will have some mobile devices which can gather some energy from the surroundings or maybe from some human-made processes. And it could involve using some physical sources, like it can be some vibrational sources. Here you can see. So this energy harvesting, we can harvest the energy from some vibrational sources, can be motion, pressure, or even electromagnetic radiation to generate some power. Or other method can be solar energy through some photovoltaic or harnessing heat through some thermoelectric effect. And it could also be used for create electricity. So already we are using some solar panel and these things. Energy harvesting might be utilized in application of some equipment which are placed in difficult to some location where it is not possible to generate power. Like in case of satellite, you can say, or in case of some area where it's difficult to generate power. So suppose some applications are there which demands too many devices to making battery replacements and which make the devices more costlier. So in that cases, energy harvesting offers numerous advantages and innovative characteristics for these wireless communication options. So this can be also possible from some thermal that options, or as my area is electromagnetic area, so I will go for this electromagnetic options where we can use this retina to harvest energy. So RF power and RF energy harvesting I can see. So energy harvesting nowadays, if you see, there are many options, but people in different area, they will go for their area, they will use their area to generate that. As my area is electromagnetic, so I am concentrating on this retina part. So as you know that RF energy, for that RF energy harvesting, our this first option is you must have, when you started this course, you must have gone through this Maxwell equations. Okay, so that Maxwell equation is there, which will help us to generate electromagnetic this devices. So what is actually this electromagnetic devices? Some electromagnetic devices which will give us electromagnetic wave, which is nothing but the combination of electric and magnetic field. So the wavelength of the generated wave, it becomes shorter with when we are increasing frequency. So when we are going for gigahertz or nowadays terahertz also applications are there, your wavelength will be reduced. And you know that the size is always related to the wavelength. So that's why we are interested for this high frequency applications. So here if you will see why I am showing this slide, this is already known to all of those who are from engineering background. Maybe they are not from C, but as this is a part of EEE also and some physics also, so that's why this is the very common slide which is normally we are using to start our that discussion in electromagnetic field. So these are the few equations, Maxwell equations, which is very important in our area. So this, based on this equation, the power, which implies that the power flow of the electromagnetic wave, it can be electromagnetically derived, and this is nothing but we can say that in case of Poynting vector, which is E cross H, electromagnetic field, that product. This implies that electromagnetic wave always carries the energy in the direction of propagating wave. So radio wave always carried both energy and information, and for that we required one transmitting antenna and one receiving antenna, and transmitting antenna is going to transmit this electromagnetic wave, whereas the receiving antenna will receive that. So based on that only, we will have this RF energy scavenging. So that is, we cannot say that it is RF energy harvesting and wireless power transfer are same thing. It's completely different thing. The RF energy scavenging and the RF energy wireless energy harvesting and wireless power transfer, it is actually the two types of RF energy scavenging. Okay. So what is actually this one? It just, we can say that when we are going for this discussion of RF energy scavenging, so we have actually two types of scavenging. One is wireless energy harvesting, the other one is wireless power transfer. So this RF energy scavenging technology, it is nothing but the capacity to transform these RF signals into electricity. Okay, the main objective of RF energy scavenging is to transfer RF energy into electricity. So how these two terms are different? The wireless energy harvesting, it is a phenomena where the incident RF power on the antenna is, normally we are going to convert it to DC power. This can be further used to drive the only low power application models. Okay. Whereas this wireless power transfer, this is actually again classified into two types. One is your near field WPT, wireless power transfer. The other one is far field. The near field wireless power transfer is non-radiative type, whereas the far field is radiative type. So in near field WPT or wireless power transfer, we employ some coils to transmit power, whereas in case of far field, we are using this antenna to emit the receive power. So what we are going to discuss, that is a far field wireless power transfer. If in detail, if suppose if we want to see the near field wireless power transfers, it actually over very small distance, when we are, we can say that if it is in millimeters, using some coils or inductive coupling, then only we are going for this near field kind of wireless power transfer. Like in wearable devices, or that you can say that to charge your, nowadays it is coming in the vehicles, you can charge your mobile also during when you are going, means you are traveling, that time you can also from your vehicle you can charge your mobile devices. So that will come under this near field wireless power transfer. Whereas the far field is actually it transmit energy across great distance, means longer working distance. You can say that where actually non-line of sight, means in wireless communication, you know that the wireless communication, it depends on somewhere we can get line of sight, like in case of rural area, whereas in urban area, we are having non-line of sight communications. So in non-line of sight communication, also we can get this facility, the RF energy power transfer facilities. So here if you see what is there in the part of this RF energy harvesting, we will have one transmitter antenna, one receiver antenna. With transmitter antenna, you can take any horn antenna or any base station antenna that we can take. What we have considered in our, we concentrated on the receiving part. So in receiving part, what we have designed, one receiving antenna along with that rectifying circuits, and plus depending on what application we are going to design that, but accordingly we will select the frequency. So what is this rectina? Again, what is this rectina? The rectina is antenna and the rectifier. Whenever you will see that some papers related to RF energy harvesting, so it is written that rectina design for RF energy harvesting application. So what is this rectina? Rectina is actually, you can say, a combined antenna with rectifier. Antenna for that same electromagnetic transmission. The rectifier is which is going to convert this RF signal into electrical energy. So along with that, when we are having antenna with rectifier, we can say that it is combinedly it will give you the rectifier, or you can say that rectina. So normally the antenna is here, which is just now I explained that we can have transmitting antenna and receiving antenna, which will launch your wave, the transmitting antenna, maybe some base station antenna. And this one, what we are going to design. So this receiving antenna, and normally it also worked on the same Friis equation principle. And you must have heard about this Friis equation, how we are going to calculate the received power. So the same Friis equation, we are going to calculate here the power. And the antenna can be isotropic antenna, which will radiate energy in all the direction, or depending on our application. If we require some directional antenna, then we can go for the directional antenna. So that is completely depend on your applications, whether you are interested for isotropic or directional antenna. So now I am not going to concentrate on this isotropic antenna. We have designed whatever I am going to show you the output, that is only for directional antenna case. So what is this rectifier circuits? So here normally we will have one receiving antenna, one impedance matching network. The rectifier will be there. the power management circuit and the application. Okay, so the device, the complete device, we can say for wireless RF energy harvesting, or for, we can say, the wireless power transfer, that is the rectina. So this is the complete circuit of the block diagram, you can say, the block diagram of the antenna. So the basic principle of this was actually the wireless energy transfer. And the rectina, it is going to have this receiving antenna which will receive the RF power. Then we will have this rectifier which consists of some nonlinear devices which will arranged in depending on your that applications. It may be for rectifying the input signal, and some DC filter required to that smoothen your DC voltage, whatever you are going to obtain. And one properly matched network should be there, which should be there to help, you can say, the rectifying circuit, which will help us to get maximum power transfer by minimizing the losses. So that is our main objective. The output DC voltage can be given to this power management circuits, again, that we have to design, which in turn is going to be used the voltage to drive some low power devices, or you can say that we are going to design this for low power sensors device or some sensor. So that's why. So this is actually, so then we are going to have that what should we check when we are going to design this rectifier. So how we will check the output. So the output, to check the output, the parameter is our power conversion efficiency. Okay, so this power conversion efficiency, if you will see, so that is actually the same formula. You can say that it depends on your effective aperture, and the power receiving power will be have effective aperture into this transmitting power, the transmitting gain by 4 pi and distance square. So that formula will be there. And now I can just show you some output depending on power conversion efficiency, how we are going to check the output. So here, if you will see this output which we are going to check, that we will have here this input power in the x-axis, and in out this efficiency in the y-axis. And we have to check the diode, what is your diode maximum efficiency. So we can have this graph for our different effect, so that we will see that how your efficiency with respect to input power is going to change. So whether your harmonics is in the required, whatever our desired requirements, depending on that or not. So these things are actually required when we are going to design some rectina for RF energy harvesting. So actually in our lab, what we have designed some rectifier antenna. So these are the different type of antenna, which is metal surface inspired structures. So I am going to discuss the first two part, not the lens one. So this one, actually it is not possible to complete all that part. So we will just discuss only this first two design. So the band which actually we have used here, mainly the 2.4 gigahertz and 5.8 gigahertz. And also for the lens to 24 gigahertz, which I cannot discuss in this limited time. And the nonlinear elements which we have used in our design, it's again Schottky diode. You must have seen that in last 2-3 days, whatever we have discussed, this means in this FDP, different speakers have discussed their design, and most of them have used these Schottky diodes. So the same thing we have used. And if the number of nonlinear elements are more, the output voltage will be higher. But again, the more number means your power conversion efficiency will be low. So depending on that, I will start the first design which we have done in our lab. This first design was for rectina for wireless energy harvesting, and it was for the dual polarized, you can say, high gain resonate cavity antenna for radio frequency energy harvesting. So here, this is our design flow. When we have designed, actually, I am going to show you two designs. One is for the frequency 5.8 gigahertz, the other one is for the 2.4 gigahertz. So the first one which we are going to show you, that design is actually for frequency. What is our first? We have to check what is your required application. The application is for our design is 5.8 gigahertz. So then how we will move to design this 5.8 gigahertz of retina. So the first step is we have to see that what unit cell you are going to use for that meta surface, because all our design was for to increase the efficiency. We have designed retina with meta surface. So this is my aperture coupled feed microstrip antenna. Then we have designed the antenna, and with PRS we have designed for 5.8 gigahertz, and this one is this aperture coupled microstrip antenna is having a, which is going to provide two different bands polarizations. So we have used two different ports. I will just show you. And here actually we have used the two layers of meta surface. In both the layer, the size, we have used a hexagonal shape of meta surface, but the size are different. Why? What is the reason? That also I will show you. So 2D meta surface, and then we have done the rectifier design for that, and finally we have done the retina measurement. So this was our design flow, and then I will just show you that this is actually, you can just see here, this is our antenna design. These are the two meta surface layer. As I told you, we have used two different layers, and both the layer we have used a different size of the hexagonal meta surface. This is our antenna view. You can see here the closer view of this antenna. So here we have taken two slots for this horizontal and vertical. So I am not going to use H and I shape word here. I will use the term like this is for my horizontal polarization and this is for vertical polarization. So this I shape, instead of using this term I shape, I will use the term vertical polarized slot. And what was the design actually? This was the top layer, and this was actually this was actually our, you can say PRS means the partially reflecting surface. We had used the partially reflecting surface here. So this is your top PRX. This is the bottom PRX. In between that, we have taken some gap, and then we have used, this is the patch. Okay, this patch is, layer is here, and then we have used two substrate, and in between that we have used the ground, and here the feed. So that's why the name is aperture coupled microstrip antenna, which was designed with two ports. So one port you can see here, that is for vertical polarization, and the other ports for that horizontal polarization. Both are all orthogonal to each other, and this correspond to each of the ports. We are having the polarization, and this is, you can see the feed here. The top substrate of ACMA, which contains this square patch with these two slots as the radiating elements. So this is actually the radiating elements. And here we have used the same that low cost substrate FR4 as many of the different, because it's easily available and the cost is also very low. So if you are doing some design for some project, you have the funding, you can go for some roser substrate. But as this one, this work we have not done for some project, it was just a PhD work. So we have used this FR4 only. But if we will do with the roser this kind of design, the losses will be less and you may get some more efficiency. Okay, so what is actually this? You can see here, we have used some gap. So this is actually the main concept is the Fabry-Parrot cavity. We have taken a lambda by 2 size of the Fabry-Parrot cavity, which is related to your frequency. So from that we calculated. So what will happen here when you are having one superstate and this is your substrate? So this is the source of the antenna and we are going to have some meta surface. So this radiation is actually, you can just see the radiation. It is radiating back and then again going. So like that, it is going to create some constructive interference. So this will help you to increase the efficiency of the antenna. So this one again, we have used this meta surface related work. So this meta surface related work means we have done this unit cell analysis. Hexagonal cell we have used. The dimensions are different for both the substrate. But here you can see that how we have analyzed this hexagonal cells. So this PRS ensures that this antenna will act as a 2D leaky wave antenna to improve the overall gain we have, and we have referred some paper where it was mentioned that if we will use some PRS structures which can behave like a 2D leaky wave kind of structure, which will help us to improve the overall gain. So in this work, we have taken a dual layer of this hexagonal loop PRS, and for that PRS actually we have used this RT Durant, which dielectric constant is 2.2, because we have tried with this FR4, but with the FR4 what we have faced the problem, the losses are very high, so the results was not good. So there is actually Roser is also providing some free some pieces of Rosers for PhD students for academic purpose. So if the PhD student can send that, they can apply it to Rosers, and only they have to handle some charges of this custom charges. So first they will send that material, and within 1 month only you can get the material. So you have to mention that what material you will get. Only few of the seats they will send. For PhD work, that is more than sufficient. So all the students, they have applied and they got some Rosers materials from that Roser corporations, and they have used in their PhD that work. So in this case also he has used, because he got this 2.2 Roser RT Durant, that F5880, and this one he used for this metasurface structures. So this is actually the equivalent circuits representation of the unit cell analysis. So we have used two layers, the layer 1 and layer 2. What will be the thickness, and then that diameter, the different dimension of hexagonal. So that this is actually heat and trial only. We did this heat and trial, no equation we have used, and this was for layer 1 and layer 2 equivalent circuits. And related to that, you can see this is your performance validations. So this is this one, the orange color, you can see this is magnitude with the help of CST and also with the help of these equivalent circuits. We checked just to verify whether it is working or not, and we got at 5.8. It's almost same. Our operating frequency was 5.8 and 6.2, so we got the same that results. The magnitude and phase both are same at this frequency for both the CST results and the equivalent circuit results. These are our PRS, what we have done here, the PRS design. So for that actually we have taken. And if you have any doubt in this that equivalent circuit, so actually the equivalent circuits, what we have done, that this Z0, if you will see, this represent your normal free space impedance, whereas this ZS we have calculated from Z0 by square root of your epsilon value. Epsilon value is, again, it depends on what substrate you have chosen. Here we have used 2.2, so from that we calculated this value, and this impedance, this inductance X1 and X2, which is for this hexagonal rings, and which is actually capacitance in nature. So this ZS represent the characteristic impedance of the top and bottom dielectric substrate, and this thickness we are having the this bottom and this substrate thickness HS, and the air gap you can see here. We have used some air gap HT within that, means in between that two layers. So that actually we have represented with the help of ZS. So the resulting superstate form this unit cell is we can say that it is a double layer non-uniform superstate, not a single layer because we have used double layer. So you can name it as a double layer non-uniform because not uniform structure are there. So non-uniform superstate. So this is actually how we have done this equivalent circuit. And here you can just see this is actually our this what you can say that magnitude distribution of unit cells. This is actually the Fabry-Parrot resonant antenna. So here, this is actually, I have already shown you that how it is going to give you the increased interference here. So this is with the help of phase distribution. On Smith chart also, we have checked that it is at 5.8. We are getting this capacitive in nature. So that also we have checked. So both this V port and H port are resonating at two frequency actually. One is at 5.8 and 6.2. So this is my magnitude distribution of unit cells. And here you can see the fabricated antenna prototype. So how it look like after fabrications. So this one is the my fabricated PRS. Here you can see that antenna is there. This one is for this Fabry-Parrot that that whatever constructive interference we got for that, this is the arrangement. We have used, this is a kind of a pipe, kind of the plastic pipes we have used. You can also, we have also tried this with the help of some sheet of thermocol that also you can put here because we required one air gap. So that air gap can also directly with the help of this, because when you are using some this plastic pipes kind of thing, so it's sometimes it is not stable. So that's why that you can see here, and means all of that sides, the that height is not uniform. So that's why it's better if you will take, because later on this picture we have taken later on during the measurement, we have used some thermal type of some units to make it stable and to make it uniform gap in between that, because that dielectric constant is also, it's negligible, so it will not affect your results. So this you can see here, we have used 2 meter surface with a different shape, and this is your antenna. The first one is your antenna, and then we are having this. Here, this is your antenna. In this picture, like this one, we have given top the antenna and this 2 meter surface. But here you can see this connector is there. This one is your antenna and this is your meter surface. This is the measurement where we have taken that in anechoic chamber. The phase constant was always uniform throughout the this structure. And this you can see the S parameter and gain results for both of that, because we actually had 2 connectors. Here you cannot see this. This is the first connector, and the other one side, one more connector is there. So here you can see these 2 connectors are there for horizontal polarization and for vertical polarization for I-shape and H-shape slots. So with the help of 2 ports, actually we got 2 resonant frequency, one at this 5.8, which is, you can see that S22, and the S11 is at 6.2. So these are our measured and simulated 2 S parameters results. And this is the realized gain, because for this isolation, like for H port, we got around 12 dBi of gain, whereas for V port, vertical polarized port, at 6.2, we got around 9 point something, which is almost 10 dBi, you can say. So the gain for both the port, it was better than 9 dBi. And this is the surface distribution at 5.8 and at 5.6.2. So what was the actually the advantage of using PRS? So the you with the help of that PRS, this one you can see the without PRS, the surface distribution, or and with the help of this PRS. So this is actually the surface distribution of 5 at 5.8 gigahertz and at that 6.2 gigahertz. So the antenna gain is without, in the absence of this PRS layer, the antenna gain was extremely low. It was around some 1 dBi, means less than 1 dBi that gain was there. Actually, we had the result, I have not included here. But with the help of this PRS, the surface distribution was better and we got around 10 to 12 dBi. So that is the advantage of using this PRS here for this, which help us to increase our gain. So this radiation pattern you can see at 5.8 gigahertz, because I already in the beginning only I told that we have, our main objective was to design directional antenna. So you can see here the copole and cross pole of the 5.8 gigahertz polarized antenna and 6.2. It's for YZ and XM plane, it is almost directive, and the cross pole is below minus 30 dB of value, which is due to that PRS only we got that this good cross polarized value. And then now we will come to this rectifier circuits for this antenna. So first, this is our step one to design the antenna. Till now, whatever we have discussed, that was my step one to design the antenna designs. The next, the second part is our the rectifier design. So rectifier design actually, because we are going to have two bands at 5.8 and 6.2. Here actually we have designed this rectifier, which was the, means we are going to receive the power from H port of the design antenna, and it is going to be used for energy harvesting application, because at 5.8 gigahertz you can get many devices. So like normally if you see many people are designed for RF energy harvesting, it is on 2.4 and 5.8 gigahertz. The second time we have done for 2.4. Most of the devices are working on Bluetooth or are 2.4 ISM band. So it's easy to get the power from, because all the in your environment you will get many devices at 2.4, and also some devices are there at 5.8. So if you want to design some RF energy harvester for this 5.8 gigahertz, so you can just follow this kind of structure. So this is actually for 5.8 gigahertz. So this one you can see our rectifier schematic and the rectifier prototype. We have for different input power, you can see the power conversion efficiency. So what is that power conversion efficiency? As in the beginning itself, I told that when you are going to design some rectifier circuits, so our main objective is to see the power conversion efficiency. The power conversion efficiency, like how we defined our efficiency. Efficiency means output by input into 100%. Like that, power conversion efficiency, we can define that it is nothing but your DC power by RF power. So RF power is my input power, which I am going to get from the antenna, and then we are going to, with the help of rectifier, we are going to convert it into DC power. So this power, which we are going to receive from H port, and then we will convert it into the, means we will receive from the H port the RF power, and we are going to convert it into the DC power. So this DC power, which across the load we will get, and the RF power will get at the H port of the antenna. So this is actually our design of the total circuits for rectifier, and across the load we are going to get this our RF power. So we have here we have designed a single stage voltage multiplier. It's a voltage doubler in our normal electronics term we are using, and this was actually then a multi-stage topology also gives a better output voltage. However, it is not suitable for low power harvesting for two reasons. You can say that why we have not used multi-stage topology, because the firstly you can see that PCA is not as, the power conversion efficiency will not as high as compared to the desired input power. The secondly, the peak of the power conversion efficiency will actually shift towards the higher powers. So that's why we can go for a single stage topology, which will give better output voltage in compared to a half wave rectifier topology, which is slightly, it will give slightly lower power conversion efficiency. So here we have used 200 nanofarad of this capacitor, which was, you can say, the series capacitor we have used. And we have selected this diode selection, which is very important when we are going to design a rectifier to get better efficiency from the rectifier circuits. So here we have used again a socket diode, which will provide the better efficiency. And it's why we socket diode, because the other speakers also inform that it's easy to get. And here we have used, there are many that provider of socket diode. We have used that Skyworks SMS7630 of socket diode with the resistance 25 ohm. This one you can just see this with a different resistance when we have checked the conversion efficiency. So here at 1 kilo ohm, you can see that conversion efficiency is very good, around 40%. So that's why we have used here 1 kilo ohm. Again, the input power, if you will see in kilo ohm, like in 1 kilo ohm, we are getting very good power. So that is the reason why we have selected here 1 kilo ohm of load. So this is our watt rectifier analysis. Okay, and this is the antenna measurement. So we have done the measurement at input power, the simulated and measurement input power. You can just see here the DC power voltage, and this one the power conversion efficiency is almost 40%, which we have already seen from that the last slide also, that with the help of that selected 1 kilo ohm of output, we got this one. Again, this one, if we will see the summary of this work, we have done a Fabry Parrot antenna with double layer of non-uniform superstrate. And we have, instead of half-wave rectifier, we have used voltage doubler rectifier. Why? The reason I have already mentioned. The conversion efficiency was almost 41%. And this can be used for RF energy harvesting with any one of the polarization, because we are going to have this horizontal as well as vertical polarizations. So that is at 5.8 and 6.2. But because at 5.8 we are getting most of the device, and now more the major objective is to get the power from the RF power, get DC power from RF power, and RF power majorly you will get at 5.8 gigahertz. So that's why we have designed at 5.8 gigahertz. Again, someone may ask that 5.8 gigahertz devices are not, you cannot get more that more number of devices. So that's why the second design is there, which was designed at 2.4 gigahertz, because 80% of devices are nowadays in wireless communication, it is going to work on 2.4 gigahertz. Okay, so that's why we have designed this one at 2.4 gigahertz. And this was actually first we designed a single antenna, and then again we have done that for this, you can say that for MIMO antennas. Okay, so that frequency is 2.4 gigahertz. Okay, and this one you can say that again the design flow is there. So the design flow, if you will see, we are going to have first we will take some dipole antenna, then we will do the designs. Means we have done the design, then antenna with some AMC we have tried, and then actually we have also tested the unit cell analysis of this AMC, and with 2D meta surfaces, then finally the same rectifier design, and then rectina measurements. So you can see here here we can see the magnetic conductor, how we have done the unit cell analysis, because our required frequency was 2.4 gigahertz. So here we have designed this that we tested the unit cell analysis with structures for AMC, and here you can see the reflection phase versus frequency at 2.4 gigahertz. We are getting almost zero phase, and similarly here also dispersion diagram if you see. So at 2.4 we are getting almost 0 degree. So this is the why we have selected this unit cell, and here you can see the results and analysis of this structure. So our main objective in this work was to design some MIMO antenna with 2x2 MIMO antenna with the help of some dipole antenna for RF energy harvesting. And that RF energy harvesting, again for both the polarization, to test that we are going to use one LED and this dipole antenna which we are going to use here. So this is actually with the help of artificial magnetic conductor, we will test this antenna. One layer of that artificial magnetic conductor we are going to use. Here if you'll see that single antenna, the dipole antenna, when we have tested, this is your AMC layer with a surface unit cell, which we have just now in the last slide we have seen. With that, this is actually the antenna design, whatever result we got. So at 2.4, you can just see here, we are getting that S parameter below minus 10 dB with a good wideband. At 2.4, the gain was almost 4.8 dBi, and this is in that antenna chamber, anechoic chamber, we have checked our antenna. The next one, our actually main objective was to design the antenna for MIMO application. So this MIMO application, if you can see here, the MIMO application, these are 4 antennas are there. These 4 antennas, actually we have designed these 4 to achieve, this MIMO antenna was designed to achieve some polarization diversity and with some isolation. So this was actually all these 4 antennas, dipole antennas are placed orthogonal to each other. You can just observe here. All these 4 antennas are placed orthogonal to each other, and the dipole arms are actually realized with copper wires, and the antenna is placed at a distance, some distance from, you can see some distance are there in between that AMC meta surface for that 4. So some gap should be there because this one we are going to design for some polarization diversity. That's why this gap is there. So this is the reason when we have checked our S11, S22, S33 and S44 for all that, because the same antenna we have used, only the difference is that they are orthogonally placed. So here actually these all are, if you will see the S parameter results, all the S parameter results are at 2.4. That S parameter, the return loss is little bit different, but below minus 15 dB for all of that 4. And if you will see this gain for all of that antenna, here the gain for all this antenna, actually this is again the that cross polarization is very less, and the copolarization is around that more than 5 dBi in all the cases. You can just see here. So now directly we will go to the rectifier. The antenna design is simple, not much that changes we have done. This is just a simple dipole antenna. So that's why I'm not going to discuss more about that. The next one, actually, you can just see here, we are going to have the rectifier, the single series. First, we will just see the single series rectifier, and then we will go for the this multiple rectifier, because for MIMO antenna we have done this multiple rectifier. Again, the same here we are going to have this torque. For that, our objective is to have a good torque conversion efficiency. So for that, if you will see the prototype here, we have used the same 1 kilo ohm of load. You can see in this picture. This is actually the input power, and this is your power conversion efficiency with a different load. For that 1 kilo ohm load, this red color you can see, we are getting more than 50% of efficiency. So again, in this design also, we have used this 1 kilo ohm of load, okay, for that 2.4 gigahertz. So for this, if you will see this power conversion efficiency, again with the help of versus the different value of load at 1 kilo ohm, you can see again we are getting more than 50% of efficiency. Okay. So this measurement, it's like there is a slight deviation in the measurement due to the uses of this substrate which we have used as fabrication during some connector fabrication, and due to that you already know that it's very difficult to get the simulation and measured results almost same. Okay, so this is actually our final Rectina prototype with DC combining. This is the measured antenna. These are all our 4 antennas which are connected to this 4 rectifier. And finally, with the help of one LED, you can see here we put one LED to check the output, whether the LED is glowing or not. With some, because 2.4 gigahertz, so we have just tested with some RF sources. Okay, so this is my final design. The summary of the work is we have used here suspended dipole antenna with simple artificial magnetic conductor at 2.4 gigahertz. And for harvesting, we have used single series topology, and that we again connected to all the 4 antennas. The power conversion efficiency was almost 55% of, and that input power is 0 dBm. It can be used for any 2.4 gigahertz of sources. And we have actually tested this with the help of an LED at each rectifier circuits and with some Wi-Fi sources. Okay, so this is my summary of the work. So I just presented 2 designs. So these are all because this kind of, we have also designed some more with the help of lens antennas and these things. You can get some publication. We have many publications related to that RF energy harvesting. Okay, so these are some references which we have used in this case. Thank you. If you have any doubt, you can ask. So,
Participants, any doubt?
Yes, 1 minute. It is actually. Yeah. Now it is audible.
Some questions, ma'am, is there?
Pardon?
No, ma'am. I'm asking if participants have any question.
Yeah. Okay.
If you have any question, ma'am is there.
So I would be happy if any questions are there.
Ma'am, in that rectifier design,
Yes.
bottom has a full ground.
Bottom is full ground. Yes.
What about a
Full
yes,
ground,
ma'am.
full
Because
ground.
you
Yes,
only
yes.
shown a top side.
No. Because actually, when the ground we are having some the partial ground, some structure, then only we used to show it. And normally, if it is full ground, then we actually show that directly that front view only. Because if the rear view, if it is full ground, means full ground, then why have to show that?
Ma'am, ma'am, good evening, ma'am.
Good
I have
evening.
one query, ma'am.
Yes.
Ma'am, in RF energy harvesting circuits, we designed the antennas with some large spaces, ma'am, spaces in dimensions, ma'am.
Correct. That is true.
But we designed this for security sensors or some other complicated designs. The entire system size only a coin size only, coin diameter only, ma'am.
Okay. You have already designed?
No, ma'am. I will learn, ma'am.
Actually, we
In
have actually tried some lens. You can see that paper is there in IEEE sensor. So that is actually the lens antenna we have tried, but it is not possible to fabricate because that one we have designed for high frequency. Like the frequency for that case was around 60 gigahertz. So
yes, ma'am.
we
Yes,
have
ma'am.
up to 40 gigahertz of facilities. So that one
They
only we have done the this simulation work, and then we submitted that. It was published already. But we are looking for that if we will get some facilities. So we can that size is actually that small in compared to what I have presented now.
Yes, thank you, ma'am.
Yeah, Dr. Sushil Kumar, you have any questions?
I think his hand is up, ma'am. So
Okay, I thought that he raised the hand. That's why I
yes,
thought
yes,
that
yes.
he may have some questions.
Anybody else having any questions for ma'am?
And whoever are that nearby BITS, Hyderabad, you are always welcome to visit our campus. If you need any kind of help in fabrication or measurement, that also you can let us know that we can help you that also.
Thank you, ma'am.
Okay.
Ma'am, kindly